So I work as a data scientist in the Alan Turing Institute, which is the British National Institute for Data Science and Artificial Intelligence. This is actually some work that I've done right before starting there. So it all started with this blog post, which was about 1.5 years ago. Developers who use spaces make more money than those who use tabs. See everyone looking very suspicious. And this was published by StackOverflow. They have a data science blog. And this guy was working in StackOverflow as a data scientist at the time. And they were looking at results from their developer survey. They run a developer survey every year. They published the results. And they found this interesting thing. So developers who use spaces make more money than those who use tabs. And if you look at the actual data underlying this, it actually checks out. It's interesting. And the thing, well, side note, all my slides are actually written in R here. Sorry. And this is the actual code that produces the plot that I'm showing. And you can run it, and you will get this plot. So really, you can go back to the original data. Yeah, a question? Well, let's keep this until the end. So this is the number of years someone coded as part of their job and their median annual salary. And in red are people who use spaces. Green and blue are the ones who use tabs or both. And you can see that it actually holds across all experience levels. Interesting. And the difference in people who use spaces is actually quite large. So what's happening there? It got picked up by mainstream media as well. Programmers who use spaces in their code get paid more. And even BBC, who should know better, programmers who use spaces are paid more. I'm really not sure what the quotation marks mean in this case. So everyone on Hacker News that read this started shouting like, oh, correlation is not causation. Because that's the thing that everyone remembers from their statistics classes. Correlation is not causation. But yeah, well, that doesn't actually tell you anything. That's just like caution. The thing is, you can go beyond that. And hopefully I will show you a bit more on how to do that. Well, correlation means just that two things appear at the same time. For example, it snows when it's cold, but that doesn't mean that if you produce snow, it will somehow get cold. That just means that these two things are, well, if you just observe them, they can be correlated. In this case, there is a causal relation. If it's really cold, it will start to snow if it rains. But how do we distinguish correlation and causation? If there is a correlation, that doesn't tell you anything if there is or isn't a causation or causal relationship. If there is no correlation, then that's probably a very strong indicator that there is no causal relationship. In this case, we have a correlation. And everyone loves a nice correlation. I did a random search in like, British tabloids, etc. Well, this is, I don't know if you have seen this website. There's a website with spurious correlations. So number of people who died by becoming tangled in their bed sheets is correlated with cheese consumption. And you can see that it holds very nicely. And if you go to this website, you'll get a lot of different correlations that are weird. Well, for me, as a statistician and a machine learning person, I see what's happening there because you have double y-axis. And that's always a reason to be cautious, because that completely changes the scale of things. Anyway, I did a search for some nice articles in British tabloids mostly. So too much exercise can kill you, especially if you are a white man. So, sorry guys here. Chocolate may help keep people slim, things like that. BBC, again, they should know better. Why going to university increases risk of getting a brain tumor. And happiness is a plate full of veg. Study finds eating your greens can help improve your outlook on life. So these are all correlations that write nice headlines that people will click on. But does it mean that when you are feeling depressed, you should just eat some broccoli? Probably not. And it's not just tabloid newspapers. This is an article published in 60s where people were claiming that crime rate, they observed that crime rate is correlated with the number of people in prisons. So their suggested solution was to release people from prisons, because that will obviously lower the crime rate. This stuff is hard. The problem is that we don't really have good language for causal data or for correlation data that doesn't imply some kind of cause. It's really hard to talk about things properly. And if you say, oh, this thing is correlated with this thing, that doesn't sound good. So that's why everyone in news, etc., goes to causal language, and everyone thinks, okay, there is a causal relation between things. So if you see something like this, what should you do? Well, you should check, first of all, if it really is a correlation or if they really mean a causation. And if you want to do something, if you want to prove a causal relation, the best way to do it is via a randomized study. Then you should check what's the sample size, because if it's too small, then all the results can be just by chance. And quite often, there is, if you see a correlation, there might be some hidden cause. And I will illustrate on an example. So, another randomly picked newspaper article. So, is your German far from your gut? Blame your DNA. Language gene accounts for nearly 50% of success in learning a foreign tongue. This is weird. So they are claiming that one gene accounts for 50% of your success in learning a foreign language. So let's look at the things that I said we should check. So is it a correlation or is it a proper randomized study showing causation? Well, if you actually read the abstract of the article, the study involved 79 first-year college students who had just arrived in the US from China, and they were learning English. And all the participants had already passed the university minimum English requirement, and 44 of them entered a 3-week course to further improve their English. And these 44 students were the ones included in the study. It's not randomized because they didn't take all the students and assign them randomly into a further course. They just picked the ones that picked it in the first place. So there are already quite a lot of things that might have influenced their decision. Maybe they are more interested in learning a foreign language, so they want to devote more time to it. And that's why they were more successful. So it's not a randomized study, so it's probably just a correlation. Small sample size. As I said, they were looking at 44 students, which is not much if you include things like genes, because that's always very messy. I did some work in bioinformatics, and it's just a nightmare. So the results might be by chance. And as I said, with genes, it's always quite difficult, because if you are looking at genes that are significantly associated with some trait, like language learning, which is a very, very complex thing, you might be doing things like testing if some gene is associated with a trait. Let's say if I was looking for a gene associated with blue eyes, I would look at all the genes and test them. Okay, does this person who has blue eyes have this variant of the gene or not? And I would do that for every gene. But the way statistical testing works, I would get a lot of results just by chance, because, well, if you are testing 20,000 genes and you have 5% error rate, you get a lot of false hits. So anytime you see a gene associated with something, it's most likely false. Is there some hidden cause in this case? Well, there might be, because the students picked themselves for the further language course. And did they learn English? Well, if we go back to the actual article, I read it, and Daily Mail claimed that students who have this variant of gene learn like 50% better than students who don't have that variant of gene. Well, this is bad reporting. If you go to the actual article that they are citing, it says something completely different. It says that this gene is correlated with white matter, like connectivity in the brain, and the students who are learning English in an intensive course had increased white matter during the course, and afterwards it went back to normal. They don't claim it increased their ability to learn a new language. And actually, they even included a plot that said, okay, it's not correlated with their results in the language course. So, how does something like this relate to the Stack Overflow result? Well, first, sample size. Well, there are actually quite a lot of people. In total, there were over 12,000 developers who answered that survey. That's statistically significant amount of people. And we can split them according to their experience levels. Well, this is a table with a lot of numbers, so let's turn it into something a bit more visual. So the darker the color, the more people. So you can see that most people in the survey were actually more junior and using tabs. And especially in the junior category, we have quite a lot of people, and then the number of people who answered the survey drops as we go along. What's interesting, the more senior people use tabs more, use spaces more than tabs. Well, anyway, the sample size seems to be quite large, so there shouldn't be a problem with that. So there is something else happening. Did we get the results by chance? In this case, I would say probably not, because we have a large sample size. Although there might be one thing to keep in mind. People were actually answering a question, what indentation do you use? And it had tabs, spaces, or both. But it doesn't say, OK, I press the tab button, but my editor changes that to spaces. What do you answer in that case? Do you use tabs or spaces? So there might be something weird with the study design in the first place. So is there some hidden cause? Now that's a bit more interesting. Is there some hidden cause that would force people to use spaces more than tabs, and that would be correlated with larger salary? Well, let's look at an example, how this kind of effect works. I don't know, in Portugal, do storks bring babies? So, that's what you tell small children. So how would we actually go about testing something like this? Well, as a data science person, you can actually look at the data and test the actual underlying hypotheses. Well, in this case, if I look at the number of stork pairs in a country and the birth rate, number of children born in a year, then you can see that these are actually correlated. And the correlation coefficient is 0.62. That's quite large correlation. And the p-value is fairly small. So as a statistician, I would reject the null hypothesis that they are not related, and I would say, OK, well, according to this, storks and babies are correlated. And if I was Daily Mail, I would say, OK, storks really do bring babies. So what's happening here? So is this the true? Well, it's always helpful to draw these sorts of diagrams, because we probably know that it's not true. And there might be something else that's correlated both with storks and with babies as well. And that forces these two to be related. So what can it be? Any guesses? Wow. Sorry? Seasons? Well, this was over the whole year, so probably not so much. Well, spoiler. Yes, exactly, the country area. Thank you. So if you look at the number of stork pairs in a country and the area of a country, you can see that these are correlated as well. And that's the underlying cause, because the size of the country is correlated both with the number of storks that are in that country and with the number of children that are born in a country. And this is the birth rate versus country area. So the area was the hidden cause, causing the storks and babies to be correlated. The thing is, in this case, the area was originally unobserved. So we had to infer something to be there. Is there something similar happening in our case? Well, hopefully we'll have a look at that. So the way to distinguish if something is really just a correlation or if there is a causal relation, in this case with storks and babies, I have a child, I know that's not true. So we had some domain knowledge. But if you don't have that much domain knowledge, you have to use some methods to actually distinguish if it's a correlation or a causation. The easiest ways to do that is through randomized testing and A/B testing, where you devise an experiment and split the data. And in the storks and babies case, it would be basically creating countries with different numbers of storks, assigning storks to countries, and then observing the birth rate, which would probably see that these two are not related. In taps and spaces, we can't really devise a randomized experiment there. The way we would do it, we would take probably people who are just learning programming and tell them, OK, you use just spaces, use just tabs, use both, and observe them 5 years on, what's their salary. Well, our domain knowledge says that probably it wouldn't make much difference, but the thing is, you can actually take observational data, like our data on StackOverflow, our data on storks and babies, and you can actually infer causation if you do it the right way, which means if you know all the variables that play a role in the situation. In our case, I had to bring in the country area to actually create the model that would explain the causation. So if you know the right variables, and if you know the structure of the model, that was the bubbles with arrows between them, then you can actually infer causation. But this is incredibly hard to do in practice, because usually you don't know all the variables that play a role in a situation, and you don't know the right model. If you knew that, you can use something called do calculus. But in this case, I assume they were not asking about all the things that could play a role in salaries and usage of tabs and spaces in the StackOverflow survey, so I can't really use that. But it's nice to keep in mind that you can actually infer causation. So I think there is some hidden cause in this case. How shall we go about finding out what it is? Well, let's start with some of the stuff that they did in the original blog post. They ran a linear regression. They were trying to predict salary using quite a lot of different input features, like the country that people are from, which affects salary, years of programming experience, if they use tabs or spaces, what developer type and language they are, front end, back end, etc. Level of formal education, contributing to open source, programming as a hobby, and company size. Looking at this, these are all the things that probably would influence salary. So if you run a linear regression using these predictors, it will tell you what weight each of these things has. And in this case, tabs and spaces usage came up as significantly affecting the salary. Well, what happens if we remove tabs and spaces? Sorry, I'm getting a bit statistical here. But what we can do, well, the thing is, if we remove tabs and spaces, and if it's really important in predicting the salary, then the model should do significantly worse than if I keep it in the model. So you can do this in a statistical way. So you can create a full model which includes the tabs and spaces usage, and the reduced model, which doesn't include tabs and spaces. So my assumption is if tabs and spaces are really, really significant in inferring people's salaries, if I remove them, the model should be terrible. And if they are not actually relevant, the model will stay the same, or the performance will stay the same, if I can just ignore tabs and spaces. So if I look at the, well, sorry, a bit more statistics. I got a comment from someone that this talk includes quite a lot of statistics and not enough machine learning, which is a bit dubious because, in my opinion, they are basically the same. It's just the cooler way to call statistics. So sorry, there will be some statistics here. If you compute something like linear regression, you can compute R squared, which is the coefficient of determination, which tells you what percentage of your data does your linear regression explain. So if I run the full model, and in this case, I should be looking at the adjusted R squared, which is like a technical adjustment for comparing different models that are nested, which means one model is a superset of the other. So my model, the full model, including tabs and spaces, can explain almost 39% of the salary data. So if I use all the information that was there on slides, 2 slides before, I can predict about 40% of the variation in the data. And if I remove the tabs and spaces information, it's the same, which means tabs and spaces are not really relevant, given all the other variables, in predicting the salary of a person. So it probably encodes for some combination of the features that I was showing you. Well, first thing to check, is there something called collinearity, which means two things that are basically the same. And if you remove one from the model, then the other will be used, vice versa, because they encode exactly the same information. In this case, there wasn't anything like that. So out of all the factors that I was showing you, nothing really correlated with tabs and spaces directly. Well, what I can do is to look at what really changed in the reduced model. When I removed the tabs and spaces from the model, some weights changed, and I can see which one changed, which means what became more important without the tabs and spaces information. So more significant in the reduced model, that means things that compensated for the absence of the tabs and spaces information, where years of programming experience, they became more important, kind of makes sense. Contributing to open source, this is interesting. So contributing to open source is important in determining the salary, and PHP. So what I found intriguing is the open source usage. So is open source related to salaries, and is open source related to tabs and spaces usage? Well, let's have a look. So this is a graph showing, again, the number of years someone coded as part of their job versus their median annual salary, and if they contribute to open source or not. So people who do contribute to open source have larger salary than people who don't. I'll do whatever you want with that kind of information. I know a lot of contributors or maintainers of open source code who would look at this graph and say, oh, people just don't contribute as much as they should, and we should probably publicize this graph a bit more. So if you contribute to open source, you have larger salary. That's probably another correlation, by the way. It's probably not a causal relation. And we can see if people who contribute to open source use spaces or tabs more. So if people don't contribute to open source, they use spaces and tabs about the same way. And if they do contribute to open source, they use spaces more than tabs. OK, so now we have a situation where people who do contribute to open source have larger salaries, and they use spaces more than tabs. Does it hold? Well, this was just for US developers. This is internationally. You can see that people who don't contribute to open source use tabs more than spaces internationally, and again use spaces a bit more than tabs. There might be some relation here because people who contribute to open source, they have to use Git, etc. And if you use spaces, the code will look exactly the same in all editors, whereas if you use tabs, it might look different across different editors for people who have different settings, or if you mix them both, that's a terrible idea. So if you do open source, there might be some reason why you would use spaces more than tabs. But, well, there might be some language effects as well. So, for example, C# developers claim to use tabs more than spaces. That's also related to open source because they're something like Ruby, people claim to use spaces more, which is nice. What I'm trying to say here is that the language is also related to if people contribute to open source or not. Because some languages have much larger open source environments than others. For example, C#, not that much, Ruby quite a lot. By the way, Ruby, you can't use tabs, so I don't know what people were doing here. So there might be some effect around language and open source. So, I'm sorry, this will be a complicated graph. So I tried to replicate the original graph showing developer salaries and years of experience, but split it based on indentation method and if people contribute to open source or not. And if open source is the driving force between the different salaries, then I should get like a random shuffling of the curves. I shouldn't get the nice effect that people who use spaces are paid more across all experience levels. In this case, the blue colors are the ones for people who use spaces, and the darker one are people who do contribute to open source, and the lighter ones are people who don't contribute to open source. So, at the top are people who do contribute to open source and use spaces. Okay, so this didn't really break up the relationship. And almost across all the experience levels, people who use spaces and don't contribute to open source are also paid more. But now it's a bit muddled because people who use both, which are the green curves, here it's a bit more similar, and there at the most senior level, people who use tabs and do contribute to open source are paid more than people who use spaces and contribute to open source as well. So, the open source contributions broke up the picture a little, but I'm looking for something that will basically move the people who use spaces a bit further down the graph, because that would be the driving force. So, open source contributions are probably one piece of the puzzle, but it doesn't really explain the difference in salaries. If it explained the difference in salaries, people who contribute to open source would be at the top of the graph, and people who don't contribute to open source would be at the bottom. This is not really the case, but it's getting there. So this was for US developers. This is internationally. Internationally, it's a bit more complicated, but the important thing is that people who use spaces, the blue ones, are still at the top most of the time. And I will explain later why I'm showing the US developers and the international information separately. So then I thought, okay, so what's actually driving the difference in salaries for people who use spaces? What I did next was I drew a density plot for, in this case, junior people who use spaces, tabs, or both. And there's a salary on the x-axis, and on the y-axis, that's basically the amount of people who fall into each bracket. And you can see that most people have their salaries around here. And that happens both for people who use spaces and for people who use tabs. But there is this weird shoulder of people who use spaces and are paid more. So what's happening there? It looks like it's not just one group of people who are just generally paid more because they use spaces, but most people who use spaces are paid the same as people who use tabs, which confirms to my intuition. But there is a group of people who are paid more and significantly more use spaces. So who are they? Well, what we can do is we can split the developers into the ones that have lower salary and larger salary and use spaces and look for things that are different from the ones that are like, in the bulk of the data. So, sorry, bear with me, there will be more statistics. No, it's morning. So I looked for things that are different for people who use spaces and are in the lower salary category and in the higher salary category. And one thing that jumped up was the version control. Well, again, that's a lot of numbers. You can see that they are getting a bit low in this case, but let's assume it's fine. So this plot shows the version control for US developers that they claim to use. And this is a proportion of people that use different version control systems and are in the lower salary bracket and in the higher salary bracket. So the red ones are people with higher salaries, or their proportion, in each of the version control categories. So in this case, you can see that the higher salary are people who use other system. I'm not sure which one that is. But the second one that has the largest proportion of people with higher salary are people that use Git. And people who use TFS or Subversion have the smallest amount of people who have higher salaries. So now we are getting somewhere. So people who use Git have, in general, higher salaries than people who, well, not in general, but there are people who use Git and have higher salary than people who use other version control systems. By the way, the numbers are getting low in this case, so take these results with a grain of salt. I did some statistical testing. In this case, on a table like this, you can use something called chi-square test, when you are basically trying to find out if the version control is independent of the split of higher versus lower salaries. It means if the proportion of people who use Git and have higher salary is significantly larger than the proportion of people who use other version control systems and have high salary. Sorry, statistics. And it came up with a p-value that's very, very small, which means I can reject the null hypothesis that they are independent, which means the version control system really does affect the salary, or the split between people with higher salaries and smaller salaries. So is version control the hidden thing here? Well, if we plot the salary against experience for Git and TFS, you can see that people who use Git are paid significantly more than people who use TFS, which is also kind of funny because you can use Git within TFS now. But it actually, yeah, it's significantly more. Let's do the plot that I did with open source as well. So this is getting, again, a bit more complicated. So the darker colors are people who use Git. The lighter colors are people who use TFS, the Foundation server. And the important thing is that, for example, if you look at the senior levels here, you will see that people, all the darker colors are the 3 top ones, and all the lighter colors are the 3 bottom ones, which means that the version control did split senior developers between those that have higher salaries and smaller salaries. It holds across some other experience levels as well. For example, in the junior ones, it's a bit more mixed up, but 6 to 10 years of experience, the darker colors are at the top. Which means if you include version control in your model, or it actually splits people into higher and lower salaries regardless of their tabs and spaces usage. So it still feels a bit counterintuitive that version control would be so important in determining people's salaries. Internationally, no, this is actually the same plot that I was showing before, and these are people who use spaces. So people who use spaces and Git are paid the most, and people who use spaces and TFS are basically at the bottom of the graph. So I managed to split the people who use spaces into lower paid category and higher paid category in this case. Internationally, yeah, it's a bit more mixed up, but still some of the things that I observed were still holding. And internationally, people are using Subversion more than TFS. So with Subversion, we are getting basically the same thing. People who use Git are paid more than people who use Subversion in this case. So why is version control so important? And together with the open source actually as well. Well, my assumption is that it actually encodes for sort of company type or company culture. Because if you are using open source, if you are using Git, if you are using a lot of like the cool new technologies, that means you are probably something like a startup that pays employees more than some normal traditional company. So that's what I sort of inferred from this. We got a couple of pieces of the puzzle. We knew that the language makes a difference, that the version control system makes a difference, contributing to open source makes a difference. But altogether, I think it encodes for a company type. But of course, this is not a very tangible thing that you can just pinpoint to. So it's not included in the developer survey. There's no variable that would encode for the sort of company culture and company type. But I believe this is the driving force behind that. If you disagree, we can discuss later. But yeah, well, sometimes you have to be a detective and sort of infer things from various pieces of the puzzle. What you can do if you are interested to play with the data yourself, you can go to this address and download all the code. This is basically just the code behind my slides, because all the plots in my slides are generated from the code. But we are not finished yet. The most important thing, can we trust the data? And in a similar way, with the Daily Mail article, I went back to the original publication and looked at the scientists were actually looking at something completely different. In this case, I was getting a bit suspicious when I was analyzing the data. Because when I plotted a salary distribution, so this is a histogram where we have salary on the x-axis and the number of people who reported that salary on the y-axis. You can see that it sort of peaked around here. But I thought, OK, but what's this weird thing in the beginning? There are a lot of people who are reporting very, very low salaries. So where are they from? What's happening there? Well, I looked at developers who reported their annual salary to be lower than $3,000. That's not much to be living on less than $3,000 a month. So most of them were from India. That's sad, but kind of what I would expect. But the second one is Poland. Poland is a normal European country. You can't live there on less than $3,000 a year. The third one is Russia. And here, for example, is Germany. Germany is a rich country. If you are working there as a developer, you are probably not paid less than $3,000 a year. So what's happening there? Well, if I plot the salary distribution for the countries that looked normal, like France, India, United Kingdom, you can see that they have a nice big bump. They are spread out. They look normal. Normal not in a statistical sense, because for normal distribution, it wouldn't have to be bounded from the bottom. But if I look at all the countries that looked a bit weird, like Russia and Germany and Poland, this is what I'm getting. So the blue one is Germany. You can see that there is one bump in the beginning, and then one big bump later on. In Poland, it's shifted because the salaries are lower, but I'm still getting a weird bump in the beginning. So people are reporting very, very low salaries, but most people are paid normally. And in Russia, most people were actually reporting the very, very low salary. So I thought, OK, that's weird. This is not how the salary distribution should look. It should look like this. So can anyone guess what's happening there? Tax? Yeah, monthly salaries. That's what I was guessing. Because, well, I was a bit cheating here because I am originally from the Czech Republic, and I have domain knowledge. Because in Czechia, when people are discussing their salary, when they are negotiating their salary in job interview, everyone always talks about their monthly salary. No one ever mentions their yearly salary. No one knows what's their salary across the whole year, because everyone always talks just about their monthly salary. So I thought, OK, yeah, that's happening there. I asked my Polish friends, and they confirmed that it's the same case in Poland. So, as I said, what's wrong? This was the question that was included in the survey. What is your current annual underlined salary in your currency, blah, blah, blah. Well, when I highlighted it to the people who were actually conducting the survey, they were saying, yeah, but it's highlighted and underlined, so of course, people answered the question that was asked. Well, the thing is, people never read things on the internet. So, when I looked at Polish salaries, for example, what I did is I fitted something called a mixture model, which fitted this lower bump and the higher bump, and gave me the estimate of the mean of each bump. And if I multiply the smaller bump by 12, I get a nice, smooth salary distribution. And the mean of the smaller bump was actually about 1/12 of the mean of the larger bump. So it really was the case. And actually, if you are doing the developer survey like this year or last year, then you may have noticed that they are asking the question differently now. They are asking for a number, and then you have to take if it's your monthly salary or yearly salary. So they did learn. So the thing is, another problem with the data is that for the salary information, most of the data is missing. So most people didn't even fill in their salary information. And that is a problem because, well, statistics has multiple types of missing data. So sorry, a bit more introduction into statistics. But the fact that the salary information here is missing is actually telling us something. If you have some missing data in a data set, there can be either missing completely at random, or missing at random, or missing not at random. I'm sorry, English here is quite hard. Missing, oh, let's go through it. Missing completely at random means there is some external process that's not related to the data at all that destroyed part of the data, like a dog eating a part of the homework or part of the survey results. In this case, I don't think there was some external process that corrupted the data and removed salary information for some random sample of the developers. It could have been some browser malfunction that actually deleted salary information for some of the developers, but probably not in this case. Then missing at random is when some part of the data is missing, and the mechanism behind the data missing is you can infer that from the rest of the data that you have. For example, a friend, that's why I was including this picture, a friend was doing some work with data from, and people were reporting online on what they were eating and what was their weight. And at some point, some people stopped reporting their weight, and you could actually infer it from the rest of the data because they basically eating more, which means they were gaining weight, so they stopped reporting that. But you could see it from their overall calorie consumption. So that's missing at random. And missing not at random is when the type of the reason why the data are missing is related to the variable that you are actually measuring. And the thing with salaries, that would be, for example, someone coming to you and asking you, how much do you weigh directly without all the other information around it? And people who have normal weight would probably respond, and people who are either overweight or severely underweight wouldn't respond. So in that case, by looking at just the data, it's impossible to see why are data missing, but it's related to the value that you are measuring there. So in this case, it would be related to the actual weight. So it's missing at random and missing not at random. It's quite difficult to distinguish. And think with salaries. If you are asking anyone for a salary or their salary information, this feels really wrong as an English sentence, but the data are typically missing at random or missing not at random. And these are like technical terms. Thing with salaries, usually people who have very high salaries don't want to disclose them, even in an online anonymized questionnaire. So, and people who have very low salaries, they can be ashamed of that, and they are hesitant to disclose that as well. So sometimes you can infer which people won't respond, sometimes you can't. So that's why it's typically missing at random or not missing not at random. And there is probably some kind of mechanism like that behind the missing data as well in the developer survey. So, as I said, we had two types of data traps in this case, and that's missing data and wrong data, because the salary information is partly missing and partly just wrong. And this can also happen accidentally or deliberately. For example, well, this really happens in real life as well. Like voter embarrassment about Trump support may have messed up poll predictions. If you remember a bit before presidential elections in the US, the polls were not showing that Trump would win. I live in the UK. All the predictions were not saying that the UK will want Brexit, etc. And part of the reason is that sometimes people are just ashamed to admit that to people who are conducting the polls. And some more historical examples, US elections in New York, mayoral elections. There was a black candidate and a white candidate, and the black candidate was looking like he would win, and in the actual elections, he completely flopped. Because people wanted to be seen as not racist, so they were saying, oh yeah, we will vote for the black candidate when people were conducting the polls. But in the actual elections, people are voting in another way. So, yeah, you can't really trust the data. You have to be paranoid if you are working with any kind of real data. And of course, data that were produced by humans, because as I said, the data can be missing. It can be missing accidentally or deliberately, and you can never be more you can never be paranoid enough. So, if you are looking at anything like this, the first question really should be: can you trust the data? And in the developer survey, you probably can't really trust it anyway. So, you can probably trust quite a lot of it on the US population, because that's where people definitely talk about just their annual salaries, and they were actually the largest group in the survey. But for all the other countries, yeah, there's only so much you can do with that. And I think this is a bit of a danger right now, where people have a lot of these like black box machine learning methods that you just call, you just give it the data, you get some results back, you use them in a production system. But in this case, the data looked fine, and some of these things, they were not spotted even by the people who were conducting the survey. So if you are using any kind of machine learning as a service, it's important to actually look at the data. And I think my main point is that with machine learning, you can do quite a lot of very cool things, but you still have to think. Well, my favorite metaphor about machine learning and data science is that all the cool models and running all the cool, like, I know, NLP, deep learning, etc., that's just tip of the iceberg. But most of the work is actually in data cleaning and data processing. And quite often you should do even more because the data are never as clean as you assume they are. My favorite joke about data science is that data science is 90% data cleaning, data wrangling, and 10% complaining about data wrangling. So this stuff is very, very annoying, but I hope you saw that it's really important because in this case, that was the salary information and the monthly salary reported. That was quite well hidden. And if I didn't know that people talk about their monthly salaries, I could have assumed that, okay, well, maybe this country just has a big tradition of unpaid internships and something like that, and that's the cause. So it's quite hard to spot these things, but it's very important to do that. So I hope you saw that just screaming correlation is not causation on Hacker News is not enough, and that you can actually go beyond that, and you can infer quite a lot of stuff even from observational data. And although correlation is not causation is true, it's never the whole story. And I hope you enjoyed this little detective story here. This was basically just my deep dive into one data set, and I hope you learned something from it on how to approach data or even how to approach news articles that are probably not true. I was joking that I should rename the job of a data scientist to a data detective, because that's how it feels quite often. So this is me as a consulting data detective. And if you have any questions, or if you want to play with the data, go on my GitHub, go on my website, and read more about it. Thank you.